Bien, nous donnons maintenant la parole aux élèves de Iași qui ont préparé une splendide vidéo sur le thème Flyovers.
The problem that we will present is named Flyovers, first names and surnames of students. Burbula Alexandra, Gabăr Sorin Gabriel, Ionita Alexandru, Pascari Tudor, Stupu Robert, and Tănase Răzvan. We are all students in the 7th grade. We learn at Costache Negruții National College from Iași. Our teacher is Adrian Zanovski. The problem was proposed by Iulian Stoleriu from Universitatea Alexandru Ioan Cuza, Iași. Presentation of the research topic. Connecting cities is essential, and when this is done, intersections can be created. We want to present how we get the minimum number of overbridges for n towns so that intersections are avoided. In order to try to get the minimum number of overbridges, we tried to solve the problem for some particular cases. And now I will let my colleague, Alexandru Ionita, to present.
2. Brief presentation of the conjectures and results obtained. A team of engineers has the task of building motorways connecting a number of towns in a certain region of the country. Any two of these towns must be connected by a single direct motorway. However, the motorways must not intersect each other. So, to achieve this, the engineers must construct a number of overbridges, which are motorway bridges that cross over another motorway. Can you help them find the minimum number of overbridges they must construct? Start with small values of n. 3. The solution. When it comes to the solution, we thought of different approaches, but our first idea was to try to find a way to connect the points that can be easily generalized. One way to do this was to start with a triangle and add points over the highest edge of the triangle. We consider that the number of flyovers is equal to the number of intersections by drawing the lines corresponding to the roads in the same plane. Firstly, we found out that we don't need any overbridges to connect 4 cities, so that any 2 cities can be connected directly. We will illustrate this through the next example. It is clear that we do not need any overbridges for 2 or 3 cities, because we can choose 2 or 3 from the previous example and connect them in the same way. Now I will let my classmate Alexandra to present the rest of the project.
Analyze the case for n equal to 5. The minimum number of flyovers connecting 5 towns is non-zero. If we denote by Fn the number of overbridges needed to connect n towns, we will have F5 equal to 1. We can prove this by using Euler's formula that says that for any planar graph, the number of vertices, V, minus the number of edges, E, plus the number of faces, F, is equal to 2. A graph can be defined as a pictorial representation or a diagram of a structure made of vertices or nodes, in our case towns, and edges, connections between edges, in our case motorways. Edges could be segments or curves. A connected graph is a graph for which there is a path from any point to any other point in the graph. A planar graph is a connected graph in the plane that can be drawn without edge crossings. When a planar graph is drawn without edge crossings, the edges and the vertices of the graph divide the plane into regions. Some of them are infinite, which are called faces. Now I will let my classmate Robert to continue.
The proof of the proposition 1 is done by contradiction. For F5, we have V equals 5, 1 for each of the vertices. E equals 10, which is calculated by adding 4 plus 3 plus 2 plus 1. So assume that F5 equals 0, because we want to know if we can connect 5 points to one another with the minimal amount of overbridge, which is 0. This means that the F5 is planar graph, and so it must satisfy Euler's formula for planar graphs. V minus E plus F equals 5 minus 10 plus F equals 2. Thus, F equals 7. As all the faces must be triangular, otherwise you could add a diagonal edge to the face. We have 3F equals 2E equals 20, and so F equals 20 over 3, contradiction. We present two ways to arrange the points in order to obtain only one overbridge for 5 points. N greater than 5. Proposition 2. T5 is not a planar graph. The minimum number of flyovers connecting N greater than 5 counts in non-zero. Proof. Indeed, if we suppose that for some N greater or equals than 6, we have Fn equals 0. Then removing one or more vertices, the same property must hold, as F5 equals 1 greater than 0. We find this to be impossible. I will let my colleague Tudor to continue the presentation.
For n equals 6, we have proposition 3. The minimum number of flyovers connecting n equals 6 towns is 3. Proof. Firstly, from the figure drawn below, we conclude that F6 less or equals 3. Suppose there exists a drawing that has 2 flyovers. Both crossings involve 4 distinct vertices. Since T6 has 6 towns, there is at least one town, say X, that finds itself at the end of both flyovers. On the other side, if we remove town X, the resulting configuration would have no flyovers. This meant that we can build a configuration of connected 5 towns with no flyovers, which is a contradiction to the demonstration from the previous point. Since we proved that we need at least 3 overbridges in order to connect 6 towns, it is enough to find an example that shows 3 overbridges are enough to connect 6 towns. We tried to generalize some of the obtained configurations in order to find the number of flyovers for bigger numbers n. The main idea was to arrange half of the points on a circle and half on the other. When n is even, we arrange the points on 2 concentric circles so that the number of points on a circle is equal to the number of points on the other circle. When n is odd, we arrange the points on 2 concentric circles so that the circle has a point more than the other. It does not matter if the bigger circle is the one that has the bigger number of points or not. Now I will let my classmate Razvan to continue the presentation.
In this way, we managed to find that the minimum number of flyovers for 7 towns is less or equal to 9, and for 8 towns is not greater than 80. These results can be observed from the following pictures. In this drawing, the black filled dots are considered cities and the empty ones are considered flyovers. So, in conclusion, to solve this problem, we used a little bit of geometry and calculus. In order to find the minimum number of overbridges, we analyzed few particular cases to grasp an idea about how to approach the problem. We also managed to find out the minimum number of overbridges for 6 towns or less, and try to generalize our ideas for more towns. Okay, this is our presentation, and thank you for your attention.
Thank you, Iași. There's no question right now. It was very interesting. Bravo.